A 400-ton aircraft is defying gravity right now, somewhere above you, and it's not magic, it's something far stranger. Most of us board a plane without really thinking about what keeps it there. We sit, we read, we accept it the way we accept that the ground doesn't fall upward. But the moment you start asking the question, really asking it, the whole thing becomes impossible. How does something heavier than a blue whale stay suspended in thin air, not for a second, for hours? The answer lies in a principle that's so old, so fundamental that we barely notice it anymore. It's called Bernoulli's principle, discovered around the 1730s by a Swiss mathematician named Daniel Bernoulli. He noticed something odd. When air moves faster over a surface, the pressure it exerts drops. Slower air pushes harder. Faster air, paradoxically, pushes less. Now, an airplane wing isn't flat. It's curved on top, flatter underneath. As the plane moves forward, air flows over that curved top surface faster than it flows under the flat bottom. And here's where the everyday miracle begins. That faster air on top creates lower pressure. The slower air underneath pushes harder. The wing gets shoved upward. But here's what people often get wrong. It's not just that one principle. Newton's third law is also at work. The wing pushes air downward. The air pushes back. Every action has an equal and opposite reaction. Both forces, pressure difference and momentum, are lifting that plane. Neither one alone could do it. But this raises a question that the earliest aviation pioneers didn't know the answer to. When you're designing a wing for the first time, how fast does the air have to move? How much curve do you need? Too little and the plane never leaves the ground. Too much and you waste fuel. The math was theoretical. Reality was uncertain. December 17, 1903. Kitty Hawk, North Carolina, Orville Wright lay prone on the Wright Flyer, a bicycle-like contraption made of wood and fabric. The engine sputtered, the propellers spun. For 12 seconds the machine stayed airborne. It traveled 120 feet. That was everything. That was proof that the math worked. But they still didn't fully understand why it worked. The Wrights were empiricists. They built, they flew, they crashed, they learned, trial and error. They had no wind tunnel data to guide them, no computer models. Just intuition and relentless experimentation. And somehow it was enough. Fast forward to today, we understand the physics far better. We have wind tunnels, computers, decades of flight data. A modern airliner wing is a masterpiece of precision. Every curve is calculated, every angle is optimized. But the fundamental principle remains unchanged. Speed creates pressure differences. Pressure differences create lift. Here's what makes it truly remarkable. That principle isn't special to airplanes. It's everywhere. A curveball in baseball curves because of pressure differences. A soccer ball dips and swerves the same way. A frisbee glides. All of them ride on the same invisible wave of physics that's been governing fluid motion since the beginning of time. But let's zoom back to the airplane. A Boeing 747 fully loaded weighs around 412 tons. That's roughly equivalent to 57 elephants. And yet it will climb to 35,000 feet today, tomorrow, every single day, multiple times a day. Somewhere right now, dozens of these giants are in the sky. The wing of that 747 is nearly 200 feet across. It needs to move through the air at a minimum speed of around 180 miles per hour to generate enough lift to overcome the plane's weight. Below that speed, called the stall speed, the pressure difference collapses. The plane falls. It's a hard boundary between flight and gravity. Pilots know this intimately. They train for it. They practice what happens when you approach that boundary and when you cross it. And yet every flight is, in some sense, a negotiation with that same limit. The engines push. The air moves fast enough. The pressure drops. The lift holds. Gravity loses. But there's another layer to this miracle. The air itself is thinner at 35,000 feet. Much thinner. There are fewer molecules to push against. So the wing has to move faster to maintain the same pressure difference. A plane cruising at altitude might be flying at 500 miles per hour, nearly 3 times the takeoff speed. This is where fuel efficiency enters the equation. The engines have to work harder to maintain that speed in thinner air, but they also burn less fuel because the air resistance, the drag, is lower. It's a delicate balance. Fly too low and you waste fuel fighting thick air. Fly too high and the air's too thin to generate lift efficiently. Airlines spend billions optimizing this. Every degree of banking, every minute of flight time, every pound of fuel matters. The route a plane takes isn't always the shortest distance between 2 points. It's the path that balances speed, altitude, fuel, and wind patterns. whether jet streams can save or cost thousands of dollars per flight. The remarkable part is that all of this, the curves, the speeds, the pressures, the calculations, emerged from one simple observation about how air behaves. A principle discovered by a Swiss mathematician in the 1730s. A principle that, for most of human history, we didn't know how to use. And now we use it to keep 400 tons aloft for hours at a time, carrying hundreds of people safely across oceans and continents. The next time you're on a flight, look out the window as you're climbing. Feel the moment when the engines push harder and the ground starts to fall away. That's not just engineering, that's physics. That's an invisible force discovered centuries ago, finally allowing us to do something that, for most of human history, seemed impossible. Subscribe so you don't miss the next everyday miracle waiting to be uncovered.